In this presentation, we are going to discuss the last two sections of the chapter 2, which are forces and circular motion and Newton's law of gravitation. And just to review what we already discussed, we discussed the motion at constant speed. We discussed also motion at constant acceleration, and this motion can be horizontal or vertical, and we say if the motion is vertical at constant acceleration, then we are talking about the free fall. Also, we describe the two-dimensional motion. We describe when the object is moving at the same time in x and y direction. Another topic we already discussed is the Newton's laws of motion, and also in the second Newton's law we discuss the concept of force, and then we can summarize the second Newton law in the equation that define force. Force equal mass times acceleration. We also review the concept of weight, and we know now weight is one type of force, and we can define the weight as the product of mass times acceleration. And now we know the weight depends of the acceleration of gravity, but the mass is always the same. Then now we know weight and mass are not the same quantity. Now we are going to describe the circular motion and what is the force that keeps that object in a circular path. Then the uniform circular motion is the motion of the object that traveling at constant speed in a circular path. Then what happens if the rocks break in this case? What happens if the rope breaks? It's going to happen what we had in the first graph, or is going to happen what we had in the second graph. What trajectory will be the ball follow, A or B? The answer is B. And the reason is the ball always will follow the tangential trajectory. Then let's review what is the concept of tangent. We can see here this line is tangent to this circle, and this line is tangent to the parabola. Then any line that is tangent to some curve will be touch the curve in one point and has the same direction of the curve. And this is the definition of tangent. Then what happens is the ball will fly off tangentially to the circular trajectory. And in this example, this is a real picture, and we can see how the sparks fly in a straight line tangentially from the edge. You can see here from the edge of the rotational grinding wheel. Then we can see here how this is always tangential. Yes, it's touched in one point and follow the direction of the grinding wheel. The reason why the object flies off tangentially to the circular path is because the velocity, the vector velocity, is always tangent as to the circular path, to the circular trajectory. As we can see in this graph, the vector velocity is always tangent to the circular trajectory. But what happened is the speed, means the magnitude of the velocity, is constant. However, the direction of the velocity is always changes in all the points. It changes. Then what happens if this object is moving in a circular path is because there is some force that keeps the object moving in this path. And we know by the second Newton law, if there is a force, then this object must have some acceleration. But why if the velocity is why if the speed is constant, the object has some acceleration? Then we know the velocity is a vector. The velocity has magnitude and direction. And in this case, the magnitude of the vector is constant, but the direction of the velocity is always changes. Then this is why in this case the acceleration is due to the change in the direction of the velocity. It's not due to the change in the magnitude of the velocity. Then the acceleration due to the changes in the velocity is called the centripetal acceleration, and is a centripetal acceleration because it's always pointing towards to the center of the circular path. Then now we want to discuss what is the magnitude of the centripetal acceleration. We know the acceleration is a vector. Then we know what is the direction of this vector. It's always points towards the center of the circle. But the magnitude of the acceleration equals to the square of the velocity, this velocity, divided by the radius of the circular path. Then this is the circular path, and this is the radius, is the distance from the center to any point of the circle. We are not going to do the math, how we can get this equation, because it's a little complicated. We need some calculus knowledge. But we are going to apply this equation to solve some problem. Then for this course, what we want to know is we can calculate the centripetal acceleration if we know the velocity of the object and the radius of the circular path. Now let's try to find the equation we can apply to calculate the force that keeps this object in a circular path. That force that keeps the object in a circular path is called the centripetal force. Then by the second Newton law, we know force equal mass times acceleration. Then now we are going to define a new kind of force. It's called the centripetal force. And this is why we had here this. This is the centripetal force. And the centripetal force equals to mass times centripetal acceleration. If we just replace or substitute the centripetal acceleration by the velocity squared divided by the radius, then we can define now the centripetal force equals to the mass of the object that is moving in a circular path multiplied by the velocity that is always tangent to the circular path divided by the radius of the circular trajectory. Because acceleration and force, they must have the same direction, then the centripetal force is always points toward to the center of the trajectory. And this is why if the centripetal acceleration is pointing to the center of the trajectory, then the force we will have the same direction as is showing here in this picture. Then these are the two equations we will apply if we need to solve any problem related to circular motion. And this is the centripetal acceleration. Remember, this is the velocity, the tangent velocity of the object. This is the radius of the circular path, and this is the mass of the object that is moving in a circular path. And now let's try to solve this problem. Then we had a 0.25 kilograms ball is attached to the end of 0.5 string and move in a horizontal circle at 2 meters per second. Then in this case we had something like that, and we had a ball that is moving. Yes, in a circular path. And what we know? We know the mass of this ball is 0.25 kilograms. And please pay attention to the units. If it's mass, then here must be kilograms. Then this is that doesn't say clearly this is the radius of the circular path, but because it's attached to the end, yes, and we know this must be, this distance correspond to the radius of the circular trajectory. Then this one will be 0.5 meters. Another thing it helps us to know this corresponds to distance is the units. Yes, 0.5 meters. And move in a horizontal circle at 2 meters per second squared. And we know this doesn't say it's the velocity, but we know by the units this is the velocity. Then we want to, this correspond to the velocity meters per second. And we want to know what is the force that keeps this ball in a circular path. And we want to know, and we want to calculate what is the force that keeps this object. Remember, the force is always point to the center of the trajectory. Then we want to calculate this force. Then we know the force, the centripetal force, mass. And you don't have to memorize this equation because I already published the equation sheet. You can use that equation sheet. And first, mass, then it's 0.0 kilograms, and please write the units also. This helps to know if you are doing something wrong. Here is the velocity. Sorry, I was writing the wrong value. It's 2.0 meters per second, and we need to square. Then square, divide. What is the radius? Radius is 0.5 meters. Then this one is 0.5 meters. And let's solve step by step. Then it's 0.25 kilograms. 2 to the second power is 2 times 2. Then it's 4. Two significant digits, and we need to square not only the number, also the units. Divide by 0.5 meters. Then now we need to check the units. This meter cancel out with one of this meter. Then now we multiply 0.25 times 4, and we will have 1.0. And let's write here centripetal force equals to 1.0, two significant digits, and what we had here is kilograms, meters, because 1 meter already cancel out, meters over second squared divided by 0.5. No units, because we already cancel out the units. Then in this, because we had here one significant digit, then 1.0 divided by 0.5 will be 2. And we had kilograms meters per second squared. This corresponds to Newton. And we know this is correct because the units for force must be Newton. And this is the answer. This is the answer. Now we are going to talk about the Newton's law of gravitation. Now we know the objects fall due to the force of gravity. This force accelerates the objects at 9.8 meters per second squared. And this is why the object has a weight, yes, which is equal to mass times acceleration of gravity. Also, the force of gravity is a field force, which means is act without any contact. And what Newton found was the Earth exerts a force on the apple, and the same kind of force that the Earth exerts on an apple is the same kind of force that the Earth exerts on the moon. Even though there is no contact, they are really far apart. Then what Newton postulated was the gravitational force that the Earth exerts on the moon is comparable with the gravitational force that the Earth exerts on an apple. Then he developed this theory, and this theory not only explains the motion of the moon around the Earth, but also explains the motion of the whole solar system. This is why this law is really important. Then after Newton analyzed a lot of experimental data, he postulated the law of gravitation. Then this law says that every two objects in the universe will attract each other by a force that is direct proportionally to the product of their masses, but is inversely proportional to the square of the distance. And let's try to understand a little more this equation. Then the gravitational force is direct proportional to the product of the masses of the two objects. Means if the object has more mass, then the gravitational force will be larger. And this is why the gravitational force, for example, between the moon and the Earth is important, is really large number, because the masses that are involved are large. But if we calculate the gravitational force between two people, then we will see this is really a small value, because the masses involved are small. Then larger masses, larger force. Yes? Now, this force is inversely proportional to the square of the distance. Then means if the objects are closer, then the force will be larger. But if the distance is increasing, then the force will be decreased. Yes, it's inversely proportional. More distance, less force. Yes, more distance, less force. Less distance, more force. And G, the upper scale G in this case is the constant of universal gravitational. Then it's just a constant. Yes, it's like the K we use in our equation is just constant of proportionality. Then there's this value. It's really a small number. It's 10 to the power minus 11. Then let's now try to solve a problem in which we need to apply the equation for force of gravitational. Then let's see. In this case, we want to calculate the force of gravitational attraction between two 60 kilograms students who are standing 1 meter apart. And in this case, what we had is we had one student. Here we had the other student, and they are apart 1 meter. Then we know this corresponds to the distance value. And the mass for this student is 60 kilograms. And the mass for the second student is also 60 kilograms. And let's write, and we want to know what is the attraction force between these two students due to the gravity. Then we know here the mass 1 is 60 kilograms. The mass 2 equals to 60 kilograms. Distance equals to 1.00 meters. Here is the constant value, which is G, 6.6, and this is always the same. Then always we need to check if we had consistent units, because we had this constant value. Then we need to check we had kilograms, we had meters, we had meters here. Then no problem, we had consistent units. Then now we can just calculate the force. And the force equals G value. Then here we will write 6.673 10 to the power minus 11 Newton multiply by mass 1, 60 kilograms, multiply, this is mass 1, by mass 2, yes, 60 kilograms, divide by the distance, but we need to square the distance. And I will try to write this problem step by step. And the force equals, you can skip some of the steps when you are solving, but here I want to show step by step. And let's multiply 60 times 60, 3600. And we multiply the numbers are also the units. Kilograms times kilograms will be kilograms squared. Divide 1 meter square will be 1. And we square the number, which is 1, and we square the units also. Now let's see what happened with the units. This kilograms cancel out with this kilograms. This meter squared cancel out with this one. And now we can see the unit we had is newtons, yes, which is consistent because it's a force, and this is the unit for a force. And now let's multiply the numbers. Then this part you can solve in the way you want. Yes, you can write this one in scientific notation, or you just can multiply the numbers. And if you multiply 6.673 times 3,600, you will get 24,012. Don't forget if you solve in this way, don't forget to write the power of 10 newtons. If you want, you can just use your calculator and just solve, multiply using your calculator. Then if we want to write this number in scientific notation and with the correct number of significant digits, then here we have 3 significant digits, 3 significant digits. Then let's write this one here with 3 significant digits will be, and let's write this one in scientific notation is 1, 2, 3, 4. And we move to the left, then we need to add 4 here. Yes, we need to add 4. Then we had, now let's write with 3 significant digits. 2.40, 10 to the power minus 11 plus 4 newtons. Why plus 4? Because we move 4 places to the left. And finally, we had here is 2.40, 10 to the power negative 7 newton. And this is really a small force. Yes, it's 10 to the power minus 7. Is we cannot notice this force. Yes, and if we are close to another person, this is the attraction force between these two people, but we cannot feel that force because our mass is small. It's really small, and this is why we cannot notice that force. You can, when you solve the problem, you can do the math in the way you want, but just you had to complete all the steps correctly. Now we are going to talk about some application of the universal gravitational law. And we know the weight is the force due to the acceleration of gravity, and we can define the wave equals to the mass multiplying by g value. What happens is close to the surface of the Earth, the wave is equal to the gravitational force. And this is why we had here in this equation. Then we can define the weight as mass times the acceleration of gravity in this case. And here we know the gravitational force. We can define a g, which is a constant value. The mass in this case, if we are consider our planet, the Earth, then mass, this small m corresponds to the mass of any of these objects, for example, or any of these animals or this person, and this corresponds to the mass of the Earth. And this, the radius corresponds to the distance from the Earth center, yes, or the radius of the Earth. Then close to the surface of the Earth, we had these two equations these two forces are equal. And what happened is if we divide by the mass, yes, and when we say this mass, the small m, this can be anything, yes, can be a car, can be elephant, can be any person. Then this is the gravitational force, for example, between the Earth and the car. Yes, and then in this case we need to consider the mass of the car. Then if we divide on both sides of the equation by the mass, by the small m, and we can see this mass cancel out. Then what we will get if we divide by the small m, and we had g on this g, which will be the acceleration of gravity, equals to the constant value g. And don't confuse these two g's. This is the acceleration of gravity, and this is a constant value. Yes. Then this corresponds to the mass of the Earth in this case, and this is the radius of the Earth. Now we can see here, we can extend this equation to calculate using the same equation. We can calculate the acceleration of gravity at any distance, yes? Because here we see G basically depend on the distance, yes, on the distance. Then we know if R is on the surface of the Earth, then the G value is 9.8 meters per second squared. But what happens if we want to calculate the distance, the G value, the acceleration of gravity at twice the distance, twice the radius of the Earth, for example? Then we can use this equation to do that. Yes, we can use this equation to do that. We can see the G value basically depends just the distance, yes, because the mass of the Earth is constant value, and we know this G is also a constant value. Then this is why, because G depends of the distance, yes, G depends basically just of the distance. This is why in our planet the G value is slightly different from one place to another, because the air is not a perfect sphere. Yes, is not perfect. The radius is not the same in all the places of our planet, and this is why here we can see some small difference between one place to another place. Also, this equation is important because we can write this equation in general, and it is possible to calculate the G value for any planet if we know the mass of the planet and the radius of the radius of that planet. Then this is why this is important, because we can write this one. It's worth for any other planet. And let's now try to solve this one problem applying this equation. When the surface of the Earth is approximately 6,400 kilometers from its center, and we know here, and this value is telling the radius of the Earth. Then we had, here is the Earth, and this is radius, and this value is equals to 6,400 kilometers. The mass of the Earth, yes, the mass of the Earth equals to 6.0 10 to the power 24 kilograms. And we want to know what is the acceleration of gravity near the surface. And we want to know what is the G value just here. Yes, just here. And we know the answer. Yes, we know the answer. We know close to the surface of the Earth, the G value is 9.8 meters per second squared. Then we expected that answer. Then we know this one because we know this is the value close to the surface. But let's see if we can get the same value using this equation. And the other thing we know is G is 6.6 to the power minus 11 Newton over kilogram squared. The next thing we need to check, we need to check the units, if the units are consistent. Then let's see, we had kilograms also here. we had kilometers, we had here meters. Then here we had a problem, is we need to get the same, we need to get consistent units. And what we had to do is we need to convert the kilometers into meters. And let's try to do this one first before to start working on the problem. Then let me write first the conversion factor we are going to apply. We know 1,000 meters. Then now in equals to 1,000 meters. And we know this is the correct way to write the conversion factor because the unit we don't want cancel out, and then we had the unit we want. And then here we can write this one is 6 and 3 more zeros, meters. And in this case, when we are working with larger numbers, what I suggest you is to use scientific notation. And let's write this number in scientific notation. Then we had here 1, 2, 3, 4, 5, 6. This is larger number, yes, positive exponent, 6 meters. And this one is 6.4 10 to the power 6 meters. And with that, we're done with this part. Now we can solve the problem. And now we can calculate the G value. What is the G value just here? Yes. Let me write there. What is the G value? Just here. And let's first write the equation. G equals to 6 point, yes, G, the constant G is 6.673 minus 11. The mass of the earth is 6.0 10 to the power 24 kilograms divided by the radius will be 6.4 meters, and we need to square this value. Yes, is this one. Then we just replace this by G. This is the mass of the earth by the mass of the earth, and then the radius 6.4 10 to the power 6, but we need to square this value. Then now let's to multiply with the numbers on top, and if we multiply the numbers on top, we had 40. First, let's check the units. This cancel out with one of this one. Yes. Then if we multiply 6.673 10 to the power minus 11 times 6.0 10 to the power 24, then if we take into account the significant digits, remember we don't take into account the significant digits of the constant, then we had two significant digits, then we had 40. Let me write this one down. 40. 24 minus 11 will be 10 to the power 13. And the units we had is Newton meter squared over kilogram. Just 1 kilogram because one of this one cancel out with this. This is what we had on top. What we had in the denominator, just be careful. You need to multiply 6 times 4. You can use your calculator to just write 6.4 10 to the power 6 squared, but also you can do in this way. 6.4 times 6.4 will be if you write the number with two significant digits will be 41. Let me write better the 41. Now we need to square everything. Now 10 to the power 6 to the second power we multiply the exponents, 10 to the power 12. And also we need to square the unit. Then remember, you need to square everything. Yes, 6.4 to the second power. If we write this number with two significant digits, will be 41. 10 to the power 6 to the second power is 10 to the power 12, and we need to square also the unit. Now this meter squared will be cancelled out with this, and if we divide these two numbers, 40 divided by 41, you will get 0.98, and now the units is Newton over kilogram. And here I forgot the power of 10, sorry. Then 10 to the power 13 minus 12 will be 1. You don't need to write 1, but let's write. Then we will have the unit. Then G value, if we write this one in standard notation, just we multiply by 10, we will have 9.8. Now the units. Yes, we already discussed about these units. Newton is kilograms. This is the definition of Newton over kilogram. And G value equals, this kilograms cancel out, meters. And this is the answer we expected. Yes, this is the G value close to the surface of the Earth. Yes, then the G value is 9.8 meters per second squared. Is the answer we expected. Then, as I said before, this equation is important because it allowed us to calculate the acceleration of gravity, not just in this point. We can calculate the acceleration of gravity at any distance. And this is why we can calculate, for example, G value if the radius of the Earth is twice, or if 3 times, or if we want to know the acceleration of gravity if the distance is 3 times the radius of the Earth. Then we can use this equation because we can see this is the mass of the Earth, which is a constant value, and this also is a constant value. Then basically G depends just of the distance. Yes? Also, we know from this equation the acceleration of gravity decreases inversely with the square of the distance. Yes? These two quantities are inversely proportional. And this is why if the distance increases, what happens with the G value, the acceleration of gravity decreases. Yes, because the relation is inverse. And if the distance or the radius increases, then the acceleration of gravity decreases. Then here we had some values just here on the surface of the Earth. The G value is 9.8, and we can see when the distance is twice the radius of the Earth, the acceleration of gravity is 2.4. If it's 3 times the radius of the Earth is 1.1. 4, then 0.6. Then we can see how this value decreases when the distance increases. And we can see also if the mass in this point is 70 kilograms, the mass is not changes. Yes, because we know the mass is the same in any location. But what happened, the weight of the object will change. Why? Because the weight depend on the G value, depend on the acceleration of gravity. If G change, if the G value change, then the weight is going to change also. And this is why the mass is constant. However, the weight change. Yes, the weight change because the G value also change. And now what we are going to do, we are going to solve a problem in 2 different ways. We are going to solve the problem applying the equation, but we are going to solve the problem also applying the proportional concept, the proportionality concept. Then let's try to solve this problem first in the first way is using the equation. Then we want to estimate the gravitational acceleration at a distance of 3 radii from Earth's center. And we want to calculate what is the G value in this point. Yes. We want to calculate the G value on this point using this equation. Then what we know, we need to know the mass of the Earth, yes, because it's here and is, let me write, it's here, then we don't need to write again. Now what is the distance in this case, or the distance in this case is 3 times the radius of the Earth. And what we had here is just the radius of the Earth. We know this distance, yes, this, but we want to calculate the acceleration of gravity if the distance is 3 times the radius of the Earth. Then let me write what information we had here. This is the mass, 6.0 10 to the power 24 kilograms. .4 10 to the power 6, and G value is 6.6 10 to the power minus 11. Then we want to know what is the distance if it's 3 times the radius of the Earth. Then let's calculate this first. Then 3 times 6.4 10 to the power 6. And this will be equal to 19.2 10 to the power 6, and here meters, yes, meters. And if we just to practice, let's write this one in scientific notation. And we move to the left, we need to add 1, yes. And if we want to write, we move 1 decimal place to the left, we need to add 1. Then this is 1.9, and if we write with 2 significant digits, yes, this is a constant value, we don't take into account that. This is 1.9 10 to the power 7 meters, and this is the distance, yes, this is this value. In this case, it's not just the radius of the Earth, it's 3 times the radius of the Earth. And now we had all we need, yes, just we can say this is the distance which we are indicated by like just R value. That means write better. Now we can calculate the G value. We had everything in the same ionics, then we don't have problem with the ionics, just calculate the G value. And it's 6.673 10 to the power minus 11 times the mass. Yes, with now this one will be 6.0 10 to the power 24 kilograms divide this one will be 1.9 10 to the power 7 meters, and we need to square this one. That part you have to really be careful. And we can see these kilograms cancel out with one of these kilograms. Yes. And now if we multiply these numbers together, we will have, we did before, will be 40, 24 minus 11, 10 to the power 13, and here Newton meter square over kilogram. Divide. Now we need to square this number, and you can square the number and the unit. Then 1.9 times 1.9 will be 3.6 if you write with two significant digits. 10 to the power 7 to the second power, just we multiply 7 times 2 is 14 a meter squared. And this cancel out. Yes. And now let me write here G equals 40 divided by 3.6 will be 11. If we write with two significant digits, then let's see if I can write better. 11. 13 minus 14 will be minus 1. Let's see if I can write better here. It's 11. 10 to the power. Let me write down. It's hard to write here. And let's write here. G equals to 11. Then 13 minus 40 is minus 1. Units. Now Newton over kilogram. And we can write this one if we write this one in standard notation, we will move one place and we will have 1.1. And we know Newton over kilograms is meters per second squared. Yes, we already did this one in the previous example. Then the G value in this case is 1.1. Then in this point, the G value is 1.1 meters per second squared. Yes. Then let me write better this one. See if I can write. This is 1.1. And this is the answer we expected. Yes, here is 3 times the radius of the Earth is 1 point. The G value of this distance is 1.1 meters per second squared. This is one way you can solve. The other way you can solve is using the proportionality constant. And let me write something like that here. Then we know by this equation, as we know, these two quantities are constant value. Yes, these two are constant value. And we can see G is inversely proportional to the square of the distance. Yes, this is. But in this case, the distance is 3 times the radius of the Earth. Yes, this is we here. Yes. Then we can say now G is inversely proportional to square. Then now we can square this one. Then G is inversely proportional to the 3 to the second power is 9 squared. What happens if the distance is increasing in 3 times, is increasing by 3 respect to this point, to the surface of the Earth, yes, is decreasing by 3 times. Then what happens is G value is going to decrease by 9. Yes, G value is going to decrease by 9. And we can calculate, and let me write here something to indicate this is now the regular G value. Yes, is some different distance. And let's write this is special. And this G value, this new G value, the value at this distance is going to decrease by 9. Yes, it's going to decrease by 9. Then if the value here is 9.8, then here the value is going to decrease, is going to be 9 times smaller. Then how we can do is we can say the G value in this point will be 9.8 meters per second squared divided by 9, because this value, which is here, is going to decrease 9 times. Yes, it's going to be 9 times smaller. Then G, if you divide 9.8 divided by 9, you will get the value is 1.1 meters per second squared. The same answer. And the same answer. And you had two different ways to solve the problem. This is the way number 1, using the equation. And this is the way number 2, using the proportionality concept. Okay. Then you had two different ways you can solve the problem, and then it's up to you how is easier for you to, in what way is easier for you to solve. The last thing I want to discuss is the relation between the gravitational force and the centripetal force. And if we attach some object to the end of any string, and this object is moving in a circular path, then we can see the force, the centripetal force that keeps that object moving in a circular path is the force we apply to the string. And this force is called the tension force. Then the centripetal force can be any force that keeps the object in a circular path. And in this case, the centripetal force is a tension force. It's the force through the string. Then now the one question is, what is the force that keeps the moon moving in a circular path around the Earth? Then the answer is that force, the centripetal force that keeps the moon moving in a circular path around the Earth is the gravitational force. Then this is why the attraction force between the moon and the Earth is the force that keeps this moon moving in this circular path. And this is going to happen if there is no gravity. Without gravity, this is the trajectory is going to follow by the moon. But if there is a gravity force, then the trajectory is the circular that is happening. Yes. Then this is all I had to discuss for today.